Good afternoon. I will explain in this brief presentation the essential part of my work. Nanotechnology currently is considered an innovative science. It is applied in many areas such as electronics, mechanics, chemistry, biology. Regarding our research object, a main question can be asked: how to reconcile the best material in order to synthesize a quantum dot of size that does not exceed a few tenths of nanometers and have good crystallinity. Here in this part, InP quantum dot has garnered great attention. Indeed, this material has many considerable advantages, such as no toxic material, low cost, and are frequently used in the manufacture of microbiological sensor, chemical sensor, solar cells, and organic transistor. Some overview about our material. It has face-centered cubic structure. The lattice parameter is 5.9 angstrom. The direct band gap of this material is 1.35 electrovolt at room temperature, and the band gap of InP quantum dot can be increased or decreased when we doped it. The outline of this presentation is broken down as follows. First of all, the synthesis of InP quantum dot and InP doped with vanadium are presented. Then the structure and morphology are detailed. Also, the optical characterization is described. Finally, I finish by conclusion and perspective. In this part, this objective will focus on the synthesis of InP quantum dot and InP quantum dot doped with vanadium by hot injection method. We focus also on the effect of vanadium on the properties of InP quantum dot, and we study the effect of this doping material on InP quantum dot. In this context, the experimental work contains the synthesis of InP quantum dot and InP doped with vanadium by hot injection method. Subsequently, the structural, morphological, and optical analyses are provided. Let us start with the XRD characteristics. So the XRD characteristic curves present that the InP and InP doped with vanadium have good crystalline quality. Also, according to this table, this result reveals that the vanadium has been incorporated into the crystal lattice of InP. According to the TM image, we summarize that the quantum dot has a spherical shape, and when we increase the concentration of doping element, the nanoparticle size of InP quantum dot are decreased. According to the high resolution term, the for InP quantum dot and InP doped with vanadium, each one has a cubic and monocrystal structure. Also, the EDX elemental mapping declared the presence of both indium phosphide and doping element in the quantum dot nanoparticle. The InP quantum dot has strong emission bands wavelength photoluminescence peak. Means it has good crystal quality, while the photoluminescence of InP doped with vanadium decreases with the increase of the concentration. Hence, the vanadium has poor effect on the optical properties of InP quantum dot. In this part, the gap energies of quantum dot solution increases with the increase in the vanadium content, and those results confirmed by the high resolution TM. In conclusion, the work carried out focuses on the synthesis of quantum dot by auto-injection method. Experimental results have shown that both the crystalline and particle size were decreased through rising in vanadium doped concentration, where the crystalline size varying from 10 and 4 nanometers. Also, we conclude that the impact of vanadium doped on the optical properties of the obtained quantum dot has been observed and investigated. Several solutions exist to compensate for the weak optical properties and the degradation of semiconductor nanocrystal, in particular InP. Hence, the formation of a shell of another semiconductor with a larger band gap on the first nanocrystal by a pentaxol growth is necessary. After that, photoelectrochemical investigation of InP quantum dot will be presented. Thanks for your attention.